Hello, so today we're going to be going over some chemical engineering calculations. So we're going to be looking at the burning of the fuel in the engine to ultimately calculate the amount of power that's output. But we're going to look at how we can calibrate the engine from the perspective of the person that's calibrating the ECU and doing the fuel mapping. So one of the first things we need to calculate is the stoichiometric air-fuel ratio, which is the perfect amount of air required to achieve a perfect burn and have no excess oxygen or unburnt fuel. Once we have that, we're going to look at calculating the air-fuel ratio, the actual air-fuel ratio, based on our lambda map. So what we can do with the lambda map is essentially tune whether we're burning fuel lean or rich. So if we're burning excess air, we're going to have more heat loss to that air in the exhaust. But if we're burning less air, we're going to have unburnt fuel. So with that, we can actually tune whether we're going to have a more economical engine at certain RPM ranges and certain load cases, or we can have more power from the engine. In order to do that, we need to consider a few things. Volumetric efficiency, this is actually something that we would get from testing the engine itself, but since we can't do that, these are just placeholder values. They're just used for the calculations. We're then going to look at how much energy is released from burning that fuel per unit mass, how much mass is going to be burnt per cycle, per cylinder, and that's going to give us the amount of heat energy that's released, and we can convert that into power. And that is going to lead us to the final table, which is going to output the power of the motorcycle at different RPMs per load. And this is going to include some other efficiencies, which we'll get to. But for now, we're going to go to the very basics, and we're going to look at breaking down the fuel composition and calculating the air-fuel ratio. So on to the calculations. So the periodic table actually has some information we need, which is related to the mass of the elements. For example, carbon has a weight of 12.011 grams per mole. I'll put a definition of what mole is up in the corner. We have hydrogen, oxygen, and nitrogen. We have these because the fuel that we're going to be considering is isooctane. And this is made up of 8 carbon atoms and 18 hydrogen atoms. When we burn this, we need to add an amount of air. So we have O2 and N2, because air is about 79% nitrogen and 21% oxygen, roughly. There's some other gases as well, but we can ignore those. When we burn that fuel with the air, we're going to get some products. Those products are going to be CO2 and H2O. And left over is also going to be nitrogen. So the first thing you want to do is calculate the amount of mass that's actually being burnt here. And I'm going to start with the air. So for air, we know that 79% is nitrogen and 21% is oxygen. And if we assume that we have 1 mole of oxygen, then we must have 3.76 moles of nitrogen. So if we want to get the mass of nitrogen, we take a look at the atomic mass. So nitrogen is 14. So if a single atom of nitrogen is 14, then 2 atoms for N2 will equal 28. But for this mole of air that we're looking at, not actually looking at a mole of nitrogen, it's a mole of air we're considering, we need to take that and multiply it by 79%. We do the same thing for oxygen. So oxygen is going to be 2 times 15.99 times by 21 over 100. So now we have the amount of mass of nitrogen in the air and the mass of oxygen in the air. But we're actually interested in the total mass of air because we're looking at the ratio of air fuel mass versus fuel mass. That gives us 28 grams per mole of air. Now the next thing we have to do is actually balance this equation to find out how many moles of air is required for a perfect burn. And from that we need to calculate the stoichiometric fuel ratio. So essentially we see we have 8 carbon atoms on the left and we can only see a single one on the right, which means we must have, if we break this down into more of a table structure, we can see we must have 8 moles of CO2 and we have 2 atoms of hydrogen here and 18 over here. So we must have 9 atoms of H2O. So from that now we need to balance the oxygen. In the CO2 we have 16 atoms of O2 and in the H2O we have 9. So that gives us 25. So let's say times 2 plus 9, so we got 25. Over here we have O2, which is 2 atoms. So if we divide 25 by 2, we get 12.5. So we know we have 12.5 moles of oxygen to burn 1 mole of C8H18, this isooctane. But we also know from the ratio of nitrogen to oxygen that we have 3.76 moles of nitrogen per 1 mole of O2. So we can say for the total moles of air, we take 12.5, 12.5 times 1 plus 3.76, and that is the total amount of moles of air required to burn this fuel. Now, our unit on the right here, our mass of air, is grams per mole. So we can multiply those together to find the total amount of grams, the total mass of air that we need to burn. That's 1,717.3 grams. And we can also now calculate the mass of the fuel. We've got H18. So if we have 8 carbon, 18 hydrogen, carbon weighs 12, hydrogen weighs 1. We can add these together and then we get 114.23 grams per mole of this isooctane fuel. Now if we actually want to calculate our stoichiometric air-fuel ratio, we can just take that 17.3, divide that by the 114.23, and we get our stoichiometric air-fuel ratio of 15.033. Now I'm going to take that value and I'm going to plug it into one of my maps just as reference, because this is the stoichiometric fuel ratio that we're going to use throughout the rest of the calculations. Okay, and here I've just put it here at the top of my actual fuel ratio map, and from there what I've done here is I've created a lambda map, which is just dummy values. I've just plugged them in because this is what you're going to do. You're going to be plugging them in to try and tune where you're getting your power and where you're being economical, and that's going to be important for producing power where you want it, but also in some cases if you want to make sure that your engine is going to pass the tests for regulations and things for emissions. So we have a lambda map and we have a stoichiometric fuel ratio, and then we actually can then make an actual air fuel ratio map. We knew that because lambda is a ratio of stoichiometric ratio to your actual fuel ratio. So we're going to be tuning how much fuel is going to be injected per cycle. So we take the stoichiometric ratio and we multiply it by the lambda value, and that gives us the actual fuel ratio. So now that we have the air-fuel ratio and we have some maps prepared, the next thing we need to do is consider the amount of energy that is actually being released from the fuel. This is going to be the high heat value and the lower heat value. Now we actually only use the lower heat value, and I'll explain why and demonstrate in this calculation. Okay, so the first thing we need to do is take the enthalpy of formation and calculate the energy that's released. We do that by simply taking the enthalpy of formation for the compound that we're considering, multiplied by the number of moles of that compound. So if we only have one C8H18, then we only need to multiply this by 1. Now we're going to balance this by products and reactants. C8H18, and then on the right hand side we have the HCO2, and we're going to have 2 different H2Os. I would like to demonstrate the difference between when H2O is liquid and when it's gas, and why we take the lower heat value and not the higher heat value. So for C8H18 we have 1 times 249, and then for CO2 we take 8 times 393, and then we take the 9 times H2O liquid, again 9 times gas. Now once we get to this point, we want to add the products together, and I should probably swap those around. So we add the products together, the CO2 and the H2O. Okay, so at this point we have the totals on one side, but we need to see the difference from before it was burnt to the release. So we take this number and we subtract the energy from the the reactant, and this is just ready now to convert to megajoules per kilogram. Although in this case it's going to be kilojoules per kilogram, and then we'll convert that one step further. So currently the mass is in grams, so we're going to convert that to kilograms. We're dividing it by 1,000. Now this is kilojoules per kilogram, and if we lock that with F4, we can just down, and then if we want to consider this megajoules per kilogram, we just divide that by 1,000 again. Now it might confuse you seeing the minus there, so it doesn't matter, we'll just make that an absolute value. Okay, so this is actually the higher heating value and the lower heating value for our iso-octane mixture. Okay, so I'd just like to explain a little bit about why we use the lower heat value instead of the higher heat value when we consider the energy that we're going to be using from that combustion cycle in the engine. Now, essentially what we're talking about here is the amount of energy that's going to be lost. We're losing the difference between lower heat value and higher heat value in the contents of the exhaust. Let me explain this point. So in our exhaust, if we have H2O, in atmospheric pressure, H2O going from 20 degrees to 100 degrees, we consider this sensible heat. We can detect this change in temperature. As we add more heat, we no longer detect that change in temperature, but we do see a change in phase from liquid to gas or steam. It's because under a gaseous state or a vapor state, water can actually contain a lot more energy, and we call this energy latent heat. So if we think of this in the exhaust, if we're comparing the energy released and the initial energy, we are losing a lot more heat energy in the exhaust if we have vapor. So the difference is essentially the latent heat when we look at the LHV and the HHV. we don't make use of the energy lost in vapor. Okay, so now we know the air-fuel ratio and the energy that will be released from our fuel when it's burnt. What we need to know now is how much air is actually being pulled into the cylinder every cycle. So for that, what we want to do is consider the displacement of the engine, which is, in this case, I'm going to say 765 cc. And we're going to say there's 3 cylinders, so it's a street triple. What a surprise. And that gives us 255 cc's per cylinder. So first off, 255 cc would be around this for a meter cubed. And the reason we want it in meters cubed is because our air density is in meters cubed. We then just need to take into account the volumetric efficiency. On the map page, I've created a map for volumetric efficiency. Essentially, what this means is our engine is not going to be perfect. It's not going to be 100% efficient at pulling in air in all conditions, especially a naturally aspirated engine. If you have a boosted engine, perhaps you'll get 100% efficiency or maybe even more. But this is going to be affected by a number of things, from the throttle opening, hence on the left we have 0 to 100%. This is relating to our throttle opening. The speed of the engine, so from 500 to 1400 RPM, it's going to start off kind of mediocre. As you go through to the mid-range, it's probably going to pick up in efficiency, and then it's going to start dying off again as the engine speed really picks up, because it's going to be start starving for air, especially when you're considering it has to push out the exhaust gas before it can refill the engine with new air. So that's where pulse tuning things can come in and help as well. From here then we need to consider the volumetric efficiency. So we take the capacity of the engine, and we'll just say this mechanical efficiency here 0.9, and then we'll times that by the air density. So this is actually how many kilograms. Sorry about that, my camera died and we're starting again in the morning. So we got to the volume in meters cubed for the displacement of the engine that we're going to be filling with air. Now when we are pumping air through the engine, because the engine is essentially an air pump, we're not going to be achieving 100% efficiency with a naturally aspirated engine, meaning it's not got turbo, it's not got a compressor or anything like this. It's just a normally aspirated engine. So in that case, we have a volumetric efficiency to consider. And that's going to be dependent on the various things like the pressure within the airbox, the geometry of the air intake, and various things relating to the mechanical side of the engine, as well as things like pulse tuning. So the exhaust is also important. So for volumetric efficiency, I created a map. On the left, we have the load, 0 to 100%. This actually represents the opening of the throttle body. So when you open the throttle, you'll have a small butterfly valve, and that will rotate, opening the pathway for air to flow. So obviously when it's a 0% opening, or when it's basically closed, idling, it's not going to be the least restrictive path for air to flow. So we get a very low efficiency. And as we open it up, efficiency increases. But it doesn't reach 100, as I said, because it's a naturally aspirated engine and there are inefficiencies. So at this point, when we want to consider the amount of kilograms of air or fuel that's going into the engine, we need to multiply the volume by the air density, and then the volumetric efficiency. That's going to tell us how much of that actual volume are we going to make use of, and how much air is going to fill that space. So now we know the mass of air per cycle. Since we know the air-fuel ratio, the actual air-fuel ratio, we can calculate the amount of fuel mass per cycle. And we can do that just by taking this value and dividing that by the actual fuel ratio at a given condition. So that's going to give us the number of kilograms per cycle of fuel. Then we can take that one step further for this one cycle. And when I say one cycle, I mean 2 revolutions of the engine, because that's going to be how many times it fires. It's going to fire once every 2 revolutions. So we take the mass of fuel and we can multiply that by, since we're working in kilograms here, let's go with kilojoules, because we want to convert to kilowatts later on. So we use this value here. It gives us 1.017 kilojoules per cycle. Okay, so the values that we're using are now kilojoules, and we want to calculate kilowatts. Kilowatts is a joule per second, so we want to start looking at this in terms of seconds. So we can convert RPM to seconds by dividing it by 60. But we also know that it's going to fire once every 2 revolutions, so we can also divide it by 2. So we can just create a formula like this. That's going to give us 116.7 revolutions per second, cycles per second. Okay, so there's one last thing to consider here. We have the amount of energy that's going to be released per cycle and the number of cycles per second. Okay, so we're working in kilograms and kilojoules, and the ultimate goal would be to calculate the power output, which is in kilowatts. And a watt is a joule per second, so a kilowatt is 1,000 joules per second. So our kilojoules is already the right unit. We just need to convert it with time. So we have 14,000 RPM. We've converted that to a number of cycles per second. So now we're on track to calculate our kilowatts. So we take the cycles per second and we multiply that by the kilojoules per cycle that we've calculated. But that's not going to be where we stop, because internal combustion engines are not so efficient at converting thermal energy into mechanical energy. That's where we have a great loss in energy. We say about 0.3 in terms of thermal efficiency. So we need to multiply this by 0.3. And then there are some other mechanical losses throughout the internals and etc, etc. So we can take that number again and multiply that by 0.9. It's going to give us 32 kilowatts. Just tidy that up a little bit. So now we've got 32 kilowatts. Not forgetting that we have 3 cylinders. So under the conditions we've just given, we get a total kilowatt output of 96 kilowatts, and we can convert that to brake horsepower if we want. So hopefully we've understood this breakdown of the calculations to get to this point. Once you understand that, you can start looking at how to put that into the maps a little bit more cleanly. I've just put some reference values here, and we can then actually build our equations into the tables. So the dummy input values are the lambda map, and then from calculating our stoichiometric ratio, we calculate our actual ratio. From the volumetric efficiency, this is one that again is another dummy input, but really we'd calculate that from testing the engine itself. And then from there we get to our heat release. Now this is going to be dependent on some of the previous values, like the actual fuel ratio. So this is where we start having our variables come into the calculations. And then of course we get to the power output as well. To make this page easier, I've got some values down here for reference. So the mechanical efficiency, the thermal efficiency, and the displacement of the engine, the number of cylinders. So that allows us to get clean output on each of these conditions. Okay, so that's it for this topic so far. We've taken our fuel, we've calculated how much air we need to completely burn that fuel, and then we've calculated the products that's going to be released. From that, we've calculated the mass required using the periodic table, balancing that equation to get the mass of air, mass of fuel, and then from that the air-fuel ratio, the stoichiometric air-fuel ratio. Based on that, we then create a lambda map, and from those two values we can calculate the actual fuel ratio, or the actual air-fuel ratio. Then we took a look at the enthalpy of formation to calculate the amount of energy that's going to be released when we burn this fuel, and that gives us the HHV, the high heat value, and the lower heat value. And we take the lower heat value, and then we considered the displacement of the engine and the efficiency of the engine to pull fresh air in. And then based on the actual fuel ratio that we've calculated, we get an amount of mass of fuel pulled in as well. And based on that mass of fuel, we calculate the energy released per ignition event per cycle. And then we just break down the RPM to calculate how many cycles we have per second and convert that to a unit of energy per second, kilowatts. Mapping this, we then get a power output chart, and we could start playing around with the numbers in our lambda map to affect this power output. So if you want to start playing around with this and seeing what happens when you change your air fuel ratio, we can start changing the lambda value, which is what the calibration engineer is going to be doing. And that's going to affect the power output. And of course, within industry, they're going to be aiming to get you past certain emissions tests. So you'll be tuning this map to be more economical, lower to mid-range, and then you'll obviously have higher power at the higher end. So if you want to play around and tune your lambda values, you'll see how you can increase the power output lower down or higher up. And then if you consider the volumetric efficiencies, there are some things that you can do. For example, people that are into tuning might be porting their engines. When you say that, they're modifying the inlet ports. And then there are more mechanical upgrades you can do, things to the intake, for example, or the exhaust that's going to affect the volumetric efficiency. Of course, this is something that we can only really play around with in this Excel unless you actually take your engine to a flow bench or something. Okay, I think this is really as far as I can take this right now. I hope you found this interesting. I hope you've learned something, especially about mapping and how this really affects your engine and how you might be able to tune it if you want to. If you do have any questions, please feel free to leave me in the comment section down below. And as always, hope you've learned something, and see you next time.